get this thing started. Control. Okay. All right. Let's go and get started. Similar announcements today than with concrete design. All the outstanding homeworks have been graded. Then there's 2 more assignments. There's homework 9.2 and 9.3. 9.2 is due on Wednesday. 9.3 is due on Friday. For exam review, we're going to do exam review on Friday, and we're going to respect the university's final exam schedule. So we're going to be doing our final exam during the allotted time slot. 10:15. It's supposed to be 10:15 to 12:15. I'm going to give you another hour just to account for computer logistical issues, things like that. As for the course evals, I've got 14 of 18 of you that have completed your course evals. If I can get everybody to complete it, I will give everybody their 10 bonus homework points. For those of you that have completed it, I've got 14 of you that completed it, but only 11 that have uploaded. If you upload your completion to Blackboard, I could give you your free 10 points on your homework assignment. So yeah. So with that, I just want to get right into it. We've been talking a lot about discretely braced beams, but we haven't talked about how to design them yet. So I want to talk about that today. And then we're going to talk about design examples with what I'm going to call low CB values. And when I say low CB values, I'm going to be honest, it's not going to make a lot of sense today, and I probably won't even mention it very much today. But on Wednesday, we'll talk about what happens when the CB values get a little high. And there's a particular thing that happens that won't become apparent today, but it'll definitely become apparent on Wednesday. But with that, let's just sort of get right into it. And I want to start our design or discussion with this. This is the flow chart. Again, like I said, probably one of the most important slides for the rest of the semester. I fixed all the LB stuff over there on the left, so that should be correct. If LB is less than LP, we're in zone 1 and our capacity is just MP. If we're between LP and LR, we're in zone 2 and we have a linear interpolated function. Zone 3, we have our elastic LTB and we use the solution we derived. Remember, zone 2 and zone 3, the equations always say it's the minimum of whatever you compute in MP because MP is your maximum. You cannot be larger than MP, so you always cut your capacity off at MP. Okay. Now, here's the thing about these equations, okay? And I posted this on Microsoft Teams, but I want to make sure that everybody's clear on this. All these equations are this, okay? It's just a graphical, it's just a flowchart representation of this graph. So this and this are saying the same thing, okay? Remember what the graph looks like. Remember, it's a constant capacity. In the zone 1, zone 2, it's linear. It's between LP and LR. And L3, we get this hyperbola. We get this curved function. We have phi mn, which is computed this way, phi mn, which is computed this way for zone 2 and zone 3. One of the other things which might seem somewhat innocuous, I used a solid point here. If you look right here on the LP expression, I used a solid point here, but I used a hollow point here. There's a reason for that, and you'll be able to see that here in a second. But the solid point tells you how you transition between full plastic and inelastic zone 1 and zone 2, and the hollow point is between zone 2 and zone 3. There's a reason why I'm showing you that, but that'll become clear here in a second. Now, designing a discretely braced beam is theoretically very difficult. Okay, and the reason why is because we got to have some sort of design aid. Without a design aid, it really just becomes throwing a dartboard at the manual and seeing which shape you hit. See, here's the problem. Each beam has its own unique curve. Like this plot here has its own unique curve. Every single shape has its own curve. See, it wasn't like that with columns. With columns, the column curve was only a function of one parameter, and that was the radius of gyration. Everything else about the column curve could be figured out with either Rx or Ry. So we had one curve for every column. With beams, that's not the case. This one curve here is a function of all sorts of different parameters for a given shape. You need the ZX, you need the SX, you need the RTS, the J, the H0 dimension. Each beam has, each curve is a function of all these different parameters. Each beam has its own curve. There's no way that we can use a single curve for every shape. We can't, because each shape has their own. So we need a design aid, okay? We need some means of making our lives a little easier. What does the manual do? Well, they give us this. And I know when you first see it, you're looking at this, you're like, oh my God, that looks horrible. I promise you it's really not. It's very, very straightforward to use, okay? This is table 3-10. I told you that there were two design aids that are going to become very critical for beams. One was the ZX tables. The other is this. It's table 3-10. If you open the FE manual, the reference manual that you get for the FE exam, you get two design aids for beams. You get the ZX chart and you get this. They give you a single sheet of one of these pages. Now, if you look at table 310, it starts on page 392, and there's pages and pages that look like this. And it looks like some Spider-Man nightmare. There's just these lines and dashed curves all over the place. It looks like a mess. But what it is just this curve for every beam all plotted on top of one another. So it's just that shape. So if you look here, you can see, like, for instance, see this black dot right there? That's the breakup between zone 1 and zone 2. And if you start flipping through these pages, you should start seeing the circular dot, the hollow dots like this, and that's the breakup between zone 2 and zone 3. So that's, again, I made a point to use that same symbology. So on the x-axis, on the horizontal axis on the bottom of the sheet, so I sort of cut it off here on the slide, like there's a gap here because I couldn't fit the entire image onto one slide and make it readable. So here on the x-axis, we have the unbraced length, we have the LB, and on the y-axis, we have our FEMN. Notice there's two different scales. We're obviously going to use the blue scale because that references LRFD. One thing to note, this design aid only works if Fy equals 50 KSI, which hasn't been a big deal and won't be a big deal in not just what we do in class, but in real life. You know, typically wide flanges have an Fy of 50 unless you got a special situation. But also CB. Notice that CB is 1. So these curves have been plotted assuming CB equals 1. And so we're going to have to take care of that when we get into designs. We have to divide our CB effect out. All right. Now, like I said, these curves look like a mess. They're really not. Okay. And I want to show you how they work. Okay. So this next slide is a bit animated, like there's animations on the slides. So everybody watch the screen, and I want to show you how table 3-10 works. Okay. So what you do with table 3-10 is the first thing that you do is you divide out the effects of CB. So you'll have some moment that you're going to design for. So you're designing a beam and you need to design for a moment of, I don't know, 500 foot kips, whatever the value is. And so you're going to look at your CB term and you're going to divide out CB. And the reason why is because the table assumes the CB value of 1. Okay. Now, the next thing that you do is you look on the x-axis and the y-axis for your point of interest. And your point of interest is the LB for whatever your problem is, for whatever your design that you're looking at. And your y is your maximum moment divided by CB. So you're going to look on the x-axis for a value and the y-axis for a value. So finally, once you do that, what you do is you look up and to the right. Okay, and find the first shape that has a solid line. Okay, and this is all going to make sense as we get into this, but I think the easiest way to go through this is to show you an example. Okay, so take a look at this box here on the bottom left. All right, we have an unbraced length of 28 feet and a moment where CB's been divided of 1162. I just made these values up, and I just want to make sure that you're comfortable using the guide. So here's what you do. On the x-axis, you go to 28 feet. On the y-axis, go to 1162. So if you, bam, that should look like this. Okay, so I'm going to go back and make sure we saw that. So X is 28, Y is 1162. Find that point, the point where they intersect. So that orange dot that I drew there on the slide, that's where an unbraced length of 28 and a moment of 1162. Okay. What you do when you found that shape is you need to look at this region, everything that's up and to the right. Okay. The reason why you're looking up and to the right is because everything that's up is a section that has a larger moment capacity than 1162. I mean, if you're designing the beam for 1162, obviously you want a section that has a capacity either equal to or higher than that. Hence why you're going up. The reason why you're going to the right is, remember, as the unbraced length goes up, the beam gets weaker. So safe sections to pick are going to be to the right. So up and to the right. Once you go up and to the right, you're going to find the first shape that has a solid line. And so looking at this slide, if I look here, you can kind of see it. There's a W18 by 175, but that's dash, W40 by 167, W27 by 146. That's the first shape that has a solid line. That's the section that I try. Okay. Now again, it's all going to become clear why we pick the solid line versus the dashed line. Let me tell you what. I'll go ahead and tell you right now why we're picking the solid line. Let me go back here. Take a look at all of the shapes in this region right here. Let's take a look at the shapes. Now, let's just read them all out. We got a W18 by 175, a W40 by 167, this W36 by 160. But take a look at the solid line. It's a W27 by 146. Somebody help me in chat. Does anybody notice something about the W27 by 146 when you compare it to all these others in this region right here? Why is the W27 by 146 solid, but the rest are dashed? What is it about that 27 by 146 that's so special? It's the lightest, exactly right. In this region, the 27 by 146 is the lightest shape, okay? So that's why we picked the solid line. The solid line in that region is the lightest shape. Now, you go to another region, and you're going to find another set of dashed and solid lines. So that's the way the plot is generated. Is it looks at those graphical regions, and it say, okay, if this is the lightest section in that region, plot it as a solid line. Okay, so it tells you as the user, this is what you need to pick. And so that would be the section that we pick for design. So I want to make sure that everybody is comfortable with this. So right now, before we do any problems, I want to look at this right here. Okay, I have an LB of 14 feet and an MU over CB of 2150. I want chat to tell me, based on these values, what's the solid line section you should pick. So I want everybody to open their manual. I want to go to table 310. I want to make sure this is comfortable. And don't worry, I have this page screen capture. I'll pull the notebook up here in a second, but I want to make sure that everybody's comfortable with this. So 14 feet, 2150 foot kits. And if you want an analogy to table 3-2, remember table 3-2, how you had a bunch of sections, but the top row was bolded and the bold row was the lightest? Well, here you've got dashed lines and solid lines, and the solid lines are the lightest. So it's kind of the same thing. So LB is 14, MU over CB is 2150. Tell me, what is the lightest section? One thing I'll help you out as you turn through table 310. If you start at the very, very beginning of table 310, you'll notice that the moments are super, super high. And then as you turn, the moments go down, so it helps you navigate. Okay, we got a W40 by 167. Let's see if that's right. So let me go to my notebook here. Let's check this out. So So this is the page that I'm on. I think it's like 3-99. Let me check on that. Let me make sure that's the right page. I think it's 99. Yeah, it's page 3-99. So it should look something like this. This is 3-99. And then what was the moment? The moment was 2150. So a 2150 moment should look, let's see, 2150 is about, like, each of these increments are 8, so probably somewhere about like right here. That's probably about right, something like that. And then LB is 14, so 14 is this. Okay, so maybe I'll do that. All right, so that's my point right there. And so what do? I go up and to the right. And so that's this one right here. And then if you're having a hard time reading it, you just follow along that curve. There's a label there. There's a label up here. Hold on, there's a label there. And you should see that's a W40 by 167. So Mr. Walker's exactly right. Is everybody else comfortable with that? And if there's any questions about that, this is important. I want to make sure you're comfortable with this. All right. Let me go back to the original screen. Okay, so like I said, this was just to make sure that we're comfortable with just the table. I just wanted to go through that. Okay, let's go through discretely braced beam design. Okay, and let's go through this step by step. Okay, so first off, step 1 is structural analysis. So we need to compute the factored moment and the associated CB value. Now, I also, when I do step 1, I tend to compute the factored shear. Again, shear really never tends to be a problem, but I just tend to go ahead and do it this step anyways. If possible, use table 3.1 for your CB value. Like, if you can get away with not computing it, don't compute it. Just use table 3.1. Next, compute your moment of inertia based on deflection limits. If you have those, be careful with your units. Don't forget your 1728 conversion factor. So after step 2, you should at least have these 3 values. You should have MU, you should have CB, and you should have your required moment of inertia. All right. What you're going to do is you're going to do what we just did. You're going to go into table 310 with LB and MU over CB and select your most economical shape. Now, again, that's only true if FY is 50 KSI, but for wide flange shapes, that's not a big deal. Now, if you pick this shape and you find that the moment of inertia isn't enough, go back to that moment of inertia table, go back to table 3.3 and pick a section from there, because you're probably not governed by strength, you're governed by your deflection limits, which is still a possibility. And then finally, analyze your section. Now, unlike with continuously braced beam design, with continuously braced beam design, if your beam was lighter than what you assumed, you really didn't need to do this. But with discretely braced beam design, you must reanalyze your beam. I cannot stress this enough. You have to recheck the beam and compute phi mn and compare that to mu. The reason why is because if your CB value is high, and we're not going to deal with this today, but we'll deal with it on Wednesday, but if your CB is high, it can generate false positives. And I don't want to get into what that means until Wednesday, because I want to keep the lecture as light as possible. But the beam and say, oh, I'm good. There's a real danger that it's not the right one. Shear capacity, you can look that up. And deflections, again, probably isn't all that necessary if you did your math appropriately. With that, I'm just going to get right into an example. Before I do, though, one quick point. Sometimes if you're picking your section in table 3.1 or 3.10, if you, this probably isn't the best slide, but if you look, there's like a lot of lines overlapping, like even some of the solid lines, because you're getting into a region where one economical section becomes changes from region to region. If you're having a hard time figuring out which line to use, instead of tracing up and to the right, you can trace upwards. Again, that only happens if the lines get crowded, but that's another way to do that. If you do that, you might have to turn from page to page to get it to work right. But that'll be, with more practice, this will become pretty doable. With that, I'm just going to get right into our example. This is a super straightforward example. We're going to design a discretely braced beam for the condition shown. It has a dead load of 1 kip per foot, a live load of 3 kips per foot. We're going to assume that the beam weighs 100 pounds per foot for its self-weight. We'll also ensure that it meets a deflection limit of L over 360. I'll go ahead and tell you, this beam is simply supported and it's uniformly distributed. So WL squared over 8 for moments, WL over 2 for shears, 5WL to the 4th over 384 EI for deflection. So I'm probably going to go through the structural analysis a little fast. I wanted to keep the structural analysis simple because I don't want that to be a barrier. I want to talk about the steel design. But this is a full-blown discretely braced beam design from start to finish. Let's just get right into it. So I'm going to share my screen. Now, before I do, what is LB for this problem? I'm going to ask chat that. What's LB? Exactly right. It's only braced at the end, so the LB is the length. It's 20. Okay, let's get right into it. Okay, so step 1 is analysis. And what I'm really after here is moments and shears. Just so everybody's aware, I'm getting a ping that my connection might be iffy. If I'm breaking up or if I need to repeat myself, just let me know in chat. All right. So we have a dead load of 1 kip per foot. We have a live load of 3 kip per foot. We have a self-weight of 100 pounds per foot, which is assumed, which we'll say is 0.1 kips per foot. And we have an L of 24 feet. Okay, so what I'm about to do, and like I'm usually a little more verbose when I write all this stuff out, but I'm going to kind of do it a little fast just because I think by now we should be pretty comfortable with this. So our M naught is WL squared over 8, which is 7.2 foot kips when you chug that out. MD is WDL squared over 8, which is 72 foot kips. I'm just going to say FPK. And then ML is WL squared over 8, which is 216 foot kips. And so MU is 1.2 M naught plus MD plus 1.6 ML. And so MU ends up being 440.64 foot kips. Again, I hope that's fine that I'm just sort of writing down the answers because I think by now we should be comfortable with that. V naught WL over 2, no L squared, just L, and it's divided by 2, so that's 1.2 kips. VD, WD L over 2, 12 kips. VL, WL over 2, 36 kips. And then VU is 1.2. VU is 73.44 kips. All right. I'm going to give everybody a sec to catch up on that because I just did a lot of writing all at once. All right. Could somebody in chat tell me, remember, here's our scenario. And we have loading that's like this. And we have bracing that's like this. This is our scenario for this problem. What is CB for that? Now remember, you can find that in table 3-1. We also did that one on a homework assignment. Everybody got a CB value for me? 1.14, exactly right. So from table 3-1, we get CB, come on, 1.14. So after step 1, we left with MU is 440.64 foot kips, VU is 73.44, and CB is 1.14. That's sort of what you want to leave step 1 with, is a design moment, a shear, and a CB. All right. Step 2 are your deflection limits. Now this problem has an allowable deflection of L over 360. So that's 24 feet over 360. And then don't forget, we need to convert that. And so 24 times 12 over 360 is 0.8 inches. And then what we'll do is we compare that to the live load deflection, which is 5 WL to the 4th over 384 EI. And again, if I'm going too fast on that, let me know. Now, what I'm going to do is I'm going to set this equation equal to 0.8 to, so 0.8 equals 5 WL to the 4th, and don't forget your 1728 over 384 EI. And I'm going to solve for I, solve for the effective moment of inertia. Okay, so pretty straightforward. So all I'm doing is just swapping the I and the 0.8. So and so when you chug this out, you should get IX minimum is 965.3 inches to the fourth. Whoop. All right. I'm going to give everybody a sec to catch up on that. Again, I hope I'm not going too fast on that. If you need a sec, you let me know. But we are making excellent time. All right. I'm going to go ahead and truck along. Again, if you need me to stop or explain something or go back, please do not hesitate. That's what chat's for. That's what I'm here for. So don't hesitate to tell me to slow down. All right. Step 3. Okay. So we know that LB, as we said in chat, LB for this problem is 24 feet. Okay. And our maximum moment divided by CB is 440.64 foot kips. And what I mean by my notation here when I say MU max, I say the maximum moment within a given unbraced segment. But this beam only has one unbraced segment, so that's just the whole beam. So that's why I have a difference there. And I'll discuss the specifics on that on the homework here in a second. Divided by 1.14. And so when you chug that out, you get 386.5. We can say 5.3, but that's, you don't need to get any more accurate than that. So here's what I want. LB is 24 feet. MU over CB is 386.5. Try a W what? I want everybody to go into table 310. I want you to go in with, remember on the x-axis it's 24, on the y-axis 386.5. I want you to tell me what section should we be using based off what's in the manual. Oh, go away. Everybody got a section for me? While you're looking that up, I'm going to see if I can screen clip this in case we need it. W18 by 76. That is exactly correct. So try a W18 by 76. Now, for those of you that are still catching up with this, okay, so I'm on page, this was on page 3-118, okay, and if you, let me, so here's the page in the manual. Let me see if I can make that bigger. Whew. Okay, there we go. So MU over CB is 386. So that's about, I don't know, maybe somewhere about like that. Oh, I can do better than that. Somewhere about like that. That's close enough. And then LB is 24. So we're looking at about right there. And so the W18 by 76. Is everybody else able to find that? Again, I'll give everybody a sec to make sure that they're good on this. Again, I don't want this design aid to scare you because it looks nasty, but it's really not. All right. I'm going to go ahead and move on. If you need me to stop and go back to something, please don't hesitate. This is what I'm here for. All right. So we have a trial shape. Could somebody tell me what's the moment of inertia? So step 4, we need to check and make sure serviceability isn't going to be an issue. If you recall, IX required for this problem was 965.3. And so that's the minimum required moment of inertia. What's the actual moment of inertia for a W18 by 76? What is that? Oh my goodness, that automatic keyboard. I'm going to have to go into my settings, see if I can get rid of that thing. What's the actual moment of inertia of a W18 by 76? $13.30. 13.30, not 130. So what that means is that our selected shape is not going to have a problem with serviceability. Okay, so this is the actual moment of inertia. So what this means is that we can go full steam ahead into step 5, which is to verify the capacity. Now, on Wednesday, we're going to do steps 3, 4, and 5 a little bit differently, and it's because the CB value is going to have a little bit of a different impact than we would have thought. But again, we're dealing with a low CB value, so that's not going to be an issue. Now, for table 3.2, so to verify the capacity, I need to go to table 3-2, and remember, we're looking at a W18 by 76. I'm going to go a little fast on this part to make sure that we complete this. I'm going to need a few values. First thing I'm going to need is LP and LR. So LP for a W18 by 76 is 9.22 feet, and LR is 27.1 feet. Now LB for this problem, if you remember, was 24 feet. So which zone are we in? Are we in zone 1, zone 2, or zone 3? Zone 2. So if we're going to do zone 2 analysis, we're going to need two more quantities. We're going to need phi and P, which I'll go ahead and tell you is 611. We're going to need phi BF, our slope, which is 12.8 kips. And while I'm at it, I'm not going to need this for zone 2 analysis, but I might as well go ahead and write it. I'm going to need the shear capacity. And the shear capacity is 232 kips. And so I got this. It's going to be pretty straightforward. Compute CP times so CB was 1.14 times 611 minus 12.8 kips times 24 feet minus 9.22 feet. And so somebody tell me, I'm going to make sure y'all are engaged. I don't want to just be doing everything. Somebody tell me, what do you get when you chug this out? Is the screen frozen? Last thing I wrote down was the equation for 2, and then the 1.14 times the quantity 611 minus 12.8 times the quantity 24 minus 9.22. It doesn't look frozen on my end, but I don't know. Let me try something. Can you see me? All right. How about now? Since I don't want to rush, but I want to make sure that we're good. Let's see if you can see this. Let's see if you can get me an answer on this. Oh man, my video is chugging out. Can you still hear me? Okay. All right. Anybody got an answer for me on this super quick? There we go. All right. There we go. So 480.87 foot kits. So therefore, and if you can't see me writing, let me know. So CMN, not min, is the minimum of CB times phi MP minus, and I'm going to say all that stuff that we just did because I'm not going to rewrite all that, or phi of p. So the minimum of that and 611. So here's the long and short of it. Phi min is 480.87 foot kips. Now somebody remind me while I'm reconnecting. Anybody got an M value? I'll tell you what. I apologize for activity issues. I don't know what's going on. Stop share because again, I apologize for these connectivity issues. So first off, then came out to be 480.87. Okay, MU is 440.64. So the beam is good from a moment capacity standpoint. As for shear, you take a look at the numbers. VVN is 232. VU was only 73. We're good on shear. And we're good on deflection, too. We can compute the deflections if we want. But we knew we needed a moment of inertia of 965, and we provided a moment of inertia of 1330. So we're good, and the answer is a W18 by 76. Now here's the kicker. This is really what the point I wanted to make at the very, very end of the problem. If you look at the assumptions on self-weight, somebody in chat remind me, what did we assume is the self-weight of the beam? So 0.1 kips per foot, not 0.01, but in pounds. What is it in pounds? Like, there's a reason why I'm saying pounds. If it's 0.1 kips per foot, it's 100 pounds per foot. Now, we assumed 100 pounds per foot. What is the actual weight of the beam that we selected? 76. There you go. So let me try and share the application again, just so we got something to look at. But here's the thing. We assumed that the beam weighed 100 pounds per foot, and it actually weighed 76 pounds per foot. So the beam is lighter than what we assumed. So if it can hold up the assumed self-weight of 100 pounds per foot, it can certainly hold itself up. So you don't need to go back and update the MU and the VU because the beam's lighter than what we assumed. If it was the other way around, we'd have to go and update that. But we don't need to do that here. So what's the answer? The answer is use a W18 by 70. So I'm just going to write that real quick. I'm hoping that works because I'm going to try and get through this part quick because I don't know what's going on with this. All right. I'm going to have to stop the share. Assignment is a little different. That instead of one, I can try. Let me just share file. Loaded on Blackboard anyways. Let's try this. Maybe this will be kinder on the bandwidth. Let's share this. Can everybody see this? Okay, good Lord. Okay, so here's the homework assignment, and if you look at the beam, there's 3 unbraced segments. There's one at the left end, one at the center, and one at the right end, but you only need to consider the central segment for the design, because if you look at the 2 segments, or the 3 segments, the one in the middle is the longest. It's the one that has the longest LB, so you only need to consider the one with LB as 12 feet, but it's not just the LB, there's also the CB values. Now let me talk about CB. In order to determine CB, if you read the first note says the self-weight of the beam may be neglected when determining CB. In other words, you are permitted to use table 3.1 to determine CB. And if you look at table 3.1, CB for a segment like this, if you look, there's CBs at the ends and CBs in the middle. And in the middle, CB is 1. On the end, CB is 1.67, but we're going to take CB as 1. So if you have a CB of 1 and you use the central segment, that's the only one you need to design for. Now, you still need to account for your dead weights and your live loads and so on and so forth for your moments. But yeah, so other than that, I think this should be pretty straightforward. I mean, there's really no more complication than what we did today, other than the formula for deflection is a bit more involved than just 5WL to the 4th over 384 EI. So watch your algebra and watch your calcs on the deflection formula. Other than that, it's pretty much the same process. What I am probably going to do, because the internet connections got so funky, I'm going to kind of go through the last few steps offline for this problem, and I'm going to post that to YouTube just to make sure that we were all good on that, because like pretty much right when I started step 5, everything started going haywire. So I'm going to redo that and post here by the end of business today and post that to the YouTube channel. I apologize for that. Any quick questions before I sign off? Like I said, I'll go through step 5 on the notebook on YouTube again, so y'all be able to copy that down. All right, well, I'm going to go ahead and turn off the recording and sign out. I will, again, post everything and update these calcs so you all have that. That's all I have for today. Again, sorry for those technical difficulties near the end, but I'll fix that with the YouTube recording. That's all I have. I will see you all on Wednesday.